So this is E658, lecture 19. In the last class, we have seen what differential nonlinearity is, or DNL, and this is nothing but the width for a code defined for a code K. It is the width of the code K minus 1 LSB divided by 1 LSB, and defined in this fashion, it is a dimensionless quantity. This, for example, if this was the ideal step, something would a real converter would probably could look like this. And the important thing to note is that this has to be, the width of the code has to be computed after all offset and gain error has been removed. The basic idea is to make a measurement on the A to D converter. You will get a plot of x versus y. You will get some kind of staircase. The steps of the staircase will not all be of the same width. Some will be wider than the other. If the converter is bad, then some steps won't be there at all. You have to jump twice as much to get to go up. And we saw that offset and gain error are typically benign problems, and which can be solved in other manners. Like in most systems, there is a negative feedback loop overall, which makes sure that the gain is what you think it is, and something to digitally correct off the offset also. After the gain and offset error have been removed from the RAM, from the staircase, then what you're left with is the best fit straight line, which probably looks like this. Once you get the best fit straight line, you know what the ideal LSB is, because once you get the best fit straight line, from the slope you'll be able to figure out what the ideal LSB is, right? And once you figure out what the LSB is, this is known, and this is known, so you can compute the DNL as a function of. So the differential nonlinearity, so to speak, is some indication of how nonlinear things are, locally, right? So if you know that in a particular region of the characteristic there is a lot of DNL, all that it means is that in that region of the characteristic, the step size vary widely from the ideal uniform step size. And in any case, DNL completely characterizes given all the widths of the codes, I can reconstruct the entire staircase. So all the DC characteristics can be gotten directly by looking at the DNL. However, a common metric which is also quoted in practice is what is called the integral nonlinearity, and this is defined. If you look at this picture, the red is the ideal staircase and the black is the real ADC characteristic, and the INL for a given code K is defined as the deviation in LSB of code transition with respect to the ideal transition that you would expect. So if the red one coincides with the black guy, then clearly the INL is 0, and any deviation will basically show up as non-zero INL. For example, if I took this is the ideal staircase. So this is code 0, 1, 2, 3, 4, 5 and so on. This is the width of code 0. This is the width of code 1. Let's say this is the kth code. What is the transition voltage to the kth code? Ideally in the ideal staircase. So the ideal transition is how much? The ideal transition will be W0 plus W1. So this is the kth code. So this is W0, W1, W2, and the width, the transition voltage for the third code will be W0 plus W1 plus W2. And if you have an ideal ADC, the widths of all the codes is the same. So how many LSBs is it? It will be, for the kth code, the transition must occur at K times LSB. In practice, it doesn't occur at K times LSB, it occurs at something else. So the INL of the kth code is simply the sum of the widths of the codes I is 0 to I is K minus 1. This is the real transition voltage. The ideal transition voltage is minus K LSB divided by 1 LSB. This is the definition of INL. It is the difference in LSBs between the measured transition to the kth code minus the ideal transition to the kth code, which simply happens to be K times LSB divided by 1 LSB. Clearly, I mean, you can see that this also depends on the widths of the codes up to the K minus 1th code. And if you kind of look at it a little carefully, if we assume all code widths are in LSBs, then INL of K is simply Wi minus, alright. What is INL of K plus 1 is nothing but 0 to K Wi minus K plus 1. So INL of K plus 1 minus INL of K is nothing but Wk minus 1, which simply is the DNL of the kth code. For example, let's consider, so basically this means that the integral nonlinearity is nothing but the running sum of differential nonlinearity. Information that is there in the DNL is there in the INL and vice versa. Alright, there is nothing, no magic about it. Then the obvious question is, if both are the same thing, then why bother to code both? So whenever you pick up an ADT converter data sheet or when you are reporting a new ADT converter, when you show measurements, these come under what are called static measurements. That is, if you put in a sufficiently slow ramp into the ADT converter, then the output will basically look like the staircase, and the shape of the staircase is what you are showing. Okay, and as I kept telling you earlier, it doesn't make sense to say the width of my kth code is 1.01 LSBs. Okay, everybody knows that you are supposed to get 1. So what is of interest is the difference between the obtained code width and the ideal code. The question is, if both of them have the same information, why bother quoting both DNL and INL? If let's say only DNL was given, the human eye cannot integrate a curve looking at it just like that. For example, we generally tend to think that if the DNL is always less than, if mod DNL is less than half an LSB, we know that the characteristic will be monotonic. But it is entirely possible, for example, in this case, let me take a converter where the quantization step is so small that you're actually not able to see the step. You're only able to see, if you look at a step-like waveform from far away, it looks like a smooth curve. A curve like this, for example, is monotonic, in the sense that there are no missing codes at all. If you go on increasing the input, the output will go on increasing. Okay, but what do you think the ideal, the INL of this curve guy will look like? What do you have to do? You have to first fit a best fit straight line. A best fit straight line probably looks like this, and so this is the analog input. This is the output code. And why they look like curves, like contiguous things, is because I'm looking at them from so far away that the steps I am not able to discern them. The INL at this code, for example, this code here is how much? It is this guy minus this guy. So this is the INL in, you should divide it down by an LSB. So, but this represents the INL of this ADT converter characteristic. But if you plot the DNL of this curve, it will turn out to be much smaller than half an LSB. The DNL doesn't have to be large for the INL to be large, because the INL is the accumulated version of the DNL. So if the DNL is of the same sign for several bits at a time, then the error in the kth code will keep accumulating. So you will end up with a situation where some code has a large deviation from the ideal code transition. Okay, case in point being this one here. So if the characteristic of the A to D looks like this, can you comment on what might be happening in the converter? If I put only, if the converter characteristic was looking like this, the ideal straight line, if I put in a sine wave, what would I get out? I will get a sine wave plus some within quotes quantization noise, because I rounded off. But if I have a converter whose characteristic looks like this, what do you think happens? You will see quantization noise corresponding to round off, but you can clearly see that this would also result in harmonic distortion. So looking at the INL will give you a reason, and if there's a lot of INL, you can expect a fair amount of harmonic distortion. And INL is indicative of the general trend of the general shape of the ADC characteristic. DNL is an indication of the local jumps of the characteristic. And as I kept saying, it's good practice to do this what is called best fit INL. A lot of people also do the following, which is called endpoint INL, which is simply they assume the ideal transition is they just short the to get the ideal straight line. What they will do is simply join this is the ideal line for endpoint INL calculation. The dotted line is just another way of defining what your ideal straight line is. And you can see that when compared to the best fit INL, what do you observe with respect to the endpoint INL? The INL that you see will be much larger and more importantly of the same sign all throughout. So when the INL is the same sign throughout, you know that I can always move my line a little and make the INL both positive and negative, thereby reducing the INL. The best fit INL is a good way of accounting for both gain error as well as offset error. If the converter had a gain error and if you did best fit INL, if you did endpoint INL, the gain error will be, it will be another straight line, but the gain error will not be removed. Best fit DNL and INL accounts for gain as well as offset errors. And depending on the application, in some applications INL can be acceptable and DNL will not be acceptable. There will be applications where, for example, in video, on your video monitors, any signal processing for video will be quite tolerant of INL, a lot of INL, but will be very intolerant of having DNL. Why? If you have observed, see the human eye is very good at capturing contrasts. But if there is a general slow trend, let's say on your TV screen, if the pink on the left side was not quite the same as the pink on the right side, you won't notice. But if there is, for example, let's say there is a missing code in the AD converter, which basically means that there is a big jump in the DNL. Then what will happen? One pixel will be, the jump in color will be, in contrast will be so much at that point that the eye will immediately catch. So the eye is very, very good at catching local variations of color. But if the shade varies uniformly slowly from one side to another, even by a large amount, you would be, the eye, it turns out, is a lot more tolerant of that kind of non-ideality than DNL. For AD converters and D2A converters, similar definitions will hold for the reverse process, which is D2A conversion. For both these things, which are involved in image processing, you will find that it's kind of reasonably tolerant of INL, but the DNL will be specified to be very tight. So it will not be uncommon to say, okay, we need an AD converter with a DNL of only 0.1 LSB, but INL you can have 5 LSB, no problem. So that might correspond to some curve like this, where you can see that there's a lot of deviation if you from the ideal transition with respect to in a whole bunch of communication receivers, INL is not at all acceptable. What happens is that in for example your cell phones, the data converters involved in the signal path should not have, DNL is kind of okay, alright, you can tolerate a poor DNL to some extent, but if you have INL, that basically turns out that it's possible to confuse the next channel for this. So in communication applications, you want to make sure that INL is small. Okay. So different applications have different requirements for INL and DNL. Some converters, of course, there are also cases like this. If I plot these are example characteristics that you might see in practice. This is on the x-axis is the input and on the y-axis is the output code. Again, the steps are not discernible because I am looking at them from far off. What is discernible, however, is these big jumps in code, and as I said, these are all what are called missing codes, and such behavior is obviously not acceptable in most situations. The other kind of thing that could happen is this guy here, and these are, what is this? This is non-monotonicity, and the big problem, I mean, this is also, you know, completely unacceptable in most applications, especially not acceptable in where? Whenever you have a negative feedback loop, okay, let's say this part, this AD converter is a part of a big negative feedback loop. Negative feedback loop is what is it doing? If the output is not equal to the input, it's going to it's going to kick something so that the output moves up. But if something in the path is not monotonic, then what will happen to the negative feedback loop? It will get confused because the computer is going to wants to go and kick something, some motor in order for something to move, okay, in one direction. So it's going to increase the code getting into the AD converter, but since the AD converter is lousy and is non-monotonic, an increment in the code to the A to D converter, I mean, or the D to A converter, in this case, will cause the output to decrease. So what is supposed to be positive, negative feedback will look like positive feedback because the slope is changing. So the negative feedback loop will get completely confused, and especially in feedback control applications. So so far we've seen this is often called low frequency characterization or static characterization of an AD converter, because the first thing you get when you get an AD converter is to put a slow ramp and make sure that the output looks like a staircase. If that is not happening, then you know that something wrong fundamentally, and then you go and fix it. It doesn't make sense to start putting high frequency sine waves and making sure something comes out when the low frequency stuff doesn't work. Alright. The next thing is spectral characterization. So this is, as you might expect, this is pretty exciting for a mathematician because of all the funny waveforms that come out, and a lot of it is simply of academic interest, because you know that quantization noise is unwanted. So it doesn't make sense to sit and go on spending your time trying to figure out all the wonderful properties of quantization noise. You want to make it, as an engineer, you want to make it as small as possible, so that you don't have to worry about it. So I'm not going to spend time obviously beating this to death. I just want to give a little bit of intuition about what you might expect when you take a Fourier transform of a quantized sine wave. The first thing, of course, is what this error is. First of all, this whole model for quantization error. You have the unquantized input, and quantization is nothing but, as you've seen, is like rounding off. The first model people thought of was to model this as some additive error. You know you're making some error. What comes out is not what goes in. So the difference is error. Now, the crucial point, that the biggest assumption that people make and often get away with in practice, is that they assume that the error is noise. It is uncorrelated with Xin. So anybody has comments on this quantization error being uncorrelated with Xin? Clearly, given Xin, I'll be able to figure out, given the characteristic of the quantizer and the input, I'll be able to figure out what the error is. So it's not noise, first of all, and definitely it depends on the input. So it being uncorrelated with the input is again an incorrect assumption. And since you made two incorrect assumptions, it doesn't hurt to make the third one, which is the quantization error is uniformly distributed in minus delta by 2 and delta by 2. Delta is the LSB. If you take the ideal straight line that we talked of in the last class and subtracted the staircase, you will get a quantization error which is bounded between, you know that the error lies between minus delta by 2 and delta by 2. And like all good engineers, we choose the easiest way out, which is we assume it's noise. So the next question is, how do you define, once you have noise, you have to define its distribution function. You just say it's uniform between minus delta by 2 to delta by 2 because it's a constant, it's easy to integrate, differentiate, all sorts of nice stuff. And then we assume that we're all right and carry on with life. It's amazing that using such completely bogus assumptions that anything works at all. But it turns out that it does. So once we made all these wrong assumptions, it's straightforward to compute everything else that we want. So the distribution of quantization noise is minus delta by 2 to delta by 2. It's a uniform random variable. When you put in a sine wave, at every instant in time you quantize, so there is a quantization error at every instant in time. You made 3 errors, you made 3 wrong assumptions, so you make the fourth one, which is you assume that the spectrum is white. So what is the mean square value of quantization noise? A uniform random variable between minus delta by 2 and plus delta by 2 has a mean square value of delta square by 12. So these 4 mistakes are the only ones you are allowed to make. Okay, after this you better make sure that you do your math properly. If I have a sine wave, if x the form A sine omega t, what is the signal to quantization noise ratio? So quantized to with an LSB size of delta. The signal to quantization noise ratio, now that you have quantized the signal, you have added, it's equivalent to adding some noise. So it makes sense to talk about the signal to quantization noise ratio. The signal power is A square by 2 for a sine wave. The noise power is delta square by 12. If I had for an n bit analog to digital converter, how many LSBs are there? How many pins are there in an n bit converter? You have the full scale range is 2 power n delta, where delta is the LSB. So what is the maximum amplitude of the sine wave? Full scale range is 0 LSB to 2 power n. The maximum value of the sinusoid that you can fit in completely into the quantizer range is 2 to the power n minus 1 times delta. The maximum signal power possible is 2 to the n minus 1 times delta whole square by 2, and noise power is delta square by 12. So the peak signal to quantization noise ratio is simply 2 to the n minus 1 delta whole square by 2 divided by delta square by 12, which happens to be, which is what? 2 to the 2n minus 2 divided by 2 times 12, which is 2 to the 2n minus 3 times 12. 12 is, I can make this 2 to the n minus 1 times 3. Alright? And when n is large, you can see that this number can become fairly large. So it's often, when you have to deal with large numbers, it's always easier to deal with in dB. So the signal to quantization noise ratio in dB is 10 log 10 because you're taking ratio of powers. Alright, if you took ratio of voltages, it must be 20 log 10. So it is 3 times 2 to the, which happens to be 6.02 n plus 1.76 e. So this is the peak signal to quantization noise ratio you can obtain when you have a sine wave going into a n bit A to D converter. So let's get some intuition as to what happens when I increase the resolution of the A to D converter by 1 bit. So if I increase the resolution of the A to D converter by 1 bit, what happens to the peak signal to noise ratio? It increases by 6 dB. So why does this increase by 6 dB make any sense? The LSB, there are many ways of thinking about it. If you want to keep the full scale range the same and you increase the resolution, that means the quantization step is now 1/2 of what it was before. So the quantization error is 1/2 of what it was before. So the quantization noise power is 1/4 of what it was before, and a factor of 4 in dB is 6 dB. This 1.76 comes about because of the sine wave, divided by the ratio of the RMS value of the sine wave to the peak. For different waveforms, if you did the same calculation for a ramp, you will find that this 1.76 is different, right? It's something else. But the key thing to note is this, regardless of the waveform that you put in, if I increase the resolution of the A to D converter by 1 bit, the signal to quantization noise ratio goes up by 6 dB. And when somebody says A is just 1 bit better than B, 1 bit in analog is 2x Okay, it's twice as better, twice as good. That's the signal to noise ratio discussion. To illustrate a couple of other points, I have chosen a dummy example, so to speak, where you are actually able to see the steps. So the fellow in blue, there is a clean sine wave in blue, and there is a quantized, the same sine wave quantized to steps of 0.1, and that staircase is actually straddling the input sine wave. Also shown in blue again is the quantization error, alright, and I have chosen the F in to be 1 by 1024 times Fs. So when I take FFT, there is no leakage and all this other stuff, alright. Naturally curious person, first thing I would do is quantize and take the FFT of look at the spectrum of the quantized output. This is what I see. Okay, I have only plotted the first 140 harmonics. In principle, I can go and plot all the 512 harmonics, right, or 511 harmonics. Okay, this is a 1024 point FFT. Now, when you had an unquantized sine wave, where were all the bins other than the fundamental? They're all they were all at minus 300 dB, were all 0. Now you can clearly see that there are a whole bunch of tones which correspond to the Fourier decomposition of the quantization error sequence. This looks quite garbled, and many would wonder if there is any intuition at all to be gained from a plot like this. It turns out that there is, and the intuition here is to notice where are the peaks occurring. I mean, if you look at the maximum peak of in this picture, around which harmonic is it occurring? Around here, right? Between about, around 60 odd, right? Between 50, 60, there seems to be a distribution. So why does that make sense? Looking at this, can you tell me why it makes sense? The spectrum of the quantized sequence is the spectrum of the ideal sine wave plus the spectrum of the quantization error. So if you look at this waveform, where do you think most of the energy will lie? The question I have asked you is, at what frequency do you think most of the quantization noise will have a peak? Looking at the temporal waveform. Okay, if I hadn't told you anything about quantization noise and said, look at this waveform here, the jagged kind of waveform, which represents, in this case, quantization noise. If I did a Fourier series on that, it will obviously it will have, any number of harmonics, right? Because it's full of discontinuities. So the question is, where will most of the energy be lying? I mean, as an engineer, what will I do? I look at this waveform, see how many count how many cycles are there. So if I kind of close my eyes a little and assume that this is all happening at uniform rate, this average frequency should be able to give me an rough indication of where most of the energy is. So let's count the number of cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, say 11, around 11 or 12 times. If there are 11 cycles here in the whole sine wave, there must be about times 4 or 5, 4, right? So it's around 44, 45 is where you would expect most of the energy, a lot of the energy to be concentrated when you expand this in a Fourier series. For this, you don't have to be a rocket scientist, right? This is just intuition you get from basic engineering. Now, to get the exact shape of the spectrum, you have to be a rocket scientist. So, as you can see, this is around where the peaks are also occurring. Of course, it's not a single peak because the frequency is not uniform. The frequency is changing. So, what does that remind you of? Where have you seen in your earlier classes, where have you seen something where the frequency is not constant but it's varying? In your basic core courses, have you seen something where the amplitude is constant and the zero crossings are changing? Frequency modulation. Okay, when you expand frequency modulated sine wave in a series, what do you get? In a Fourier series, what do you get? Basically, if you take a sine wave FM modulated and do a Fourier analysis on it, the Fourier coefficients will all be Bessel functions. So it turns out that, not surprisingly, if you try and go and compute all the Fourier coefficients of this quantization noise, you can express them in Bessel series, and this is a general truth, but that unscientific way of calling this waveform is it's periodically periodic. So there's local periodicity and there's certainly overall periodicity with this large period. This happens in many situations in real life. I mean, FM is a kind of a very synthetic example that happens in electrical engineering. The moon goes around the earth and the earth goes around the sun. So the position of the moon itself is also periodically periodic, and this is how Bessel functions were discovered, if you didn't know. The Bessel functions came about because people were trying to study the moon and what happens to it, and the angular position of the moon is also periodic. It's periodic with some 29 days or something. It turns around, but the Earth takes 365 days, okay, around the sun. So there is this double periodicity, all right, and you see Bessel functions there. You see Bessel functions in FM, and you see Bessel functions in quantization noise, because they're all fundamentally the same, similar physical. I mean, the shape of the waveform looks not similar. So I will stop with that